My name is Aris Panos. I'm an econometrician. And let me start by motivating some of the things that I'll be talking about. What is unique about econometrics is that every applied economist knows exactly how the economy works. I'm being serious. And they have different models, of course, but each model is true for the individual in each case. And that makes it very, very difficult to take a lot of their evidence seriously. So there is a whole attitude about modeling in econometrics is you define what we call a structural model or a substantive model, and then you feed it to the data. And the data have only one job, to give you numbers for the coefficients. And of course, that gives no chance to the data to object to the theory, and there is the testing is really not testing the theory at all, because it doesn't give the data a chance. So coming from that stable, I had to find different ways to explain what can go wrong in this kind of setup, and why the evidence they end up with is really highly questionable. So here I have the contents of the paper, and of course, there's no way I'm going to go through all of that. So just to give you some idea of what's in the paper, and if you are interested, send me an email, and I'll be happy to share the paper with you. I will focus on the underlying themes, and hopefully I will finish at least some of them to give you a good idea of what this is all about. So let me start with the summary, because this is my chance to give you the conclusions as well. The discussion is basically putting forward what I think of as a unifying framework for frequentist inference in an attempt to pinpoint the potential errors that could undermine the reliability of inference. To that end, I introduce a number of different distinctions that cause major confusions, especially in econometrics. The first is the distinction between pre-data and post-data error probabilities. P-value is a post-data error probability. Type 1 and type 2 is pre-test error probability. And confusing the two can create all kinds of problems. Yes, mathematically, they're related, but the underlying reasoning behind each one of them is different. And I'm going to make a case that if we want to go beyond p-values and accept reject rules, we really need to work with post-data error probabilities. And severe testing proposed by Deborah Mayo is such an error probability. The second distinction is between modeling and inference phases of statistical analysis. As I'm going to tell you later on, we are posing very different questions to the data. So confusing the modeling part with the inference part is like confusing constructing a boat on preset specifications with running it in a race. Yes, the two are related, but the questions you pose and the answers you're seeking are very different. The third distinction, which caused a lot of confusion about significance testing, is the distinction between testing within a statistical model versus testing outside the model. When you do model validation, you are not testing inside the boundary of the model, you're testing outside. And it's a completely different ballgame. But significance testing can be used for both. And it's the source of major confusions there. And finally, this is especially important for econometrics, people confuse a statistical model, which I define to be all the probabilistic assumptions you impose on your data, nothing else, and the substantive model, which comes from some theory. The two are related. As I'm going to explain later on, you choose a parameterization of your statistical model to ask the questions of interest. So there is a parametric embedding involved. But the crucial point is that if your statistical model is invalid, in other words, you did impose invalid probabilistic assumptions on your data, it's pointless to talk about how good your structural model is, because the tools you're using are not giving you reliable answers. So, in relation to the current discussions about reproducibility and replicability, I have major doubts that the PPV and the various other measures being used come anywhere close to giving us answers to the questions relating to that. From my perspective, this replicability, reproducibility crisis is really an untrustworthiness of evidence problem. We think that if you cannot reproduce it, something is wrong with the previous study. If we focus on the trustworthiness of the evidence, we get a very different answer. So here I have a quotation from a very recent paper in an RSS journal, which basically says, the crisis in statistics is a microcosm of the crisis in science. It's the mechanical application of methods without understanding their assumptions, limitations, or interpretation will surely reduce scientific replicability. And I totally agree with that. I will go a step further. I will argue that a lot of bad evidence are easily reproducible and replicable. Every week, thousands of MBA students confirm what they call the efficient market hypothesis. They take the same data or similar data, they test the hypothesis using the same bad statistical methods, and they end up with the same results. It has nothing to do with replicability. So in 1995, I took them to task, took their data, tested the underlying assumptions. They were all wrong. There were 5 assumptions. Every one of them was wrong. Respecified the model, tested the efficient market hypothesis, and the answer was negative. All those replicable results were just a waste of time. They were based on false assumptions forced on the data. So I totally disagree with my fellow Greek, Yannis Ioannidis, on blameworthiness by association, and 20% of all nulls are non-nulls, and things of that sort. If you want to test whether certain evidence are valid or invalid, you look at paper by paper and see the different ways it could have been wrong, and then see whether the authors did a good job to actually prevent all those errors. Now, part of the problem is this gap between practitioners and theoreticians. But I'm not going to go into that, because one is doing mathematics. They don't care about their assumptions. But the other is using the methods without knowing whether they are really applicable or relevant or appropriate for his or her data. But I have a long discussion in the paper for those interested. So, frequencies testing. One of the most important distinctions that helped me enormously clear up the fog is this distinction between testing within, which is figure 1, and testing outside the boundaries. The big square is the set of all possible statistical models that could have given rise to this particular data. When you choose a model, you choose a tiny subset. When you do Neyman-Pearson testing, you split that into 2, or you should think of it that way, and you are testing within. But that, of course, assumes your model is valid. Because if the true model is somewhere else, you're looking at the wrong place. Now, on the other side is testing outside. Then now there is your model is valid. But then the alternative is chaos. Yes, it could be some other model somewhere outside. And misspecification testing is designed to test your model against all the rest. And of course, it raises technical issues, and one has to be very careful what you can infer in a misspecification test. So I'm going to show you some examples to realize that in both cases we can use significance testing. If we are focusing on testing within, significance testing is not different from name-of-Pearson testing. It just has a point null. But when you do misspecification testing, you don't have a clearly defined power and everything else that goes with it. So we take shortcuts in misspecification testing, and there are different shortcuts that one has to be very careful about. At the center of everything, of course, is the notion of a statistical model, first introduced in 1922 by R.A. Fisher. He was very clear about what the basic model is. He called it an infinite population, but the idea is exactly the same. But the model itself is defined in terms of the distribution of the sample, which means you really need to dig out all the assumptions. This is very crucial if you're interested in model validation. You have to test all your assumptions, not some of them or leave some out and so on. So over the years, I came up with specifications of different well-known models using a complete list of testable probabilistic assumptions, not errors, not something that you think is okay. Here is the simple normal model, 4 assumptions. If any of the 4 assumptions are invalid, you have to be very careful with your inferences. Now, usually we write the model as is in 2 or 1 there, but it's not very clear what is it that we have to test. It's the 4 assumptions I said before. So, as I said before, testing within implicitly assumes a partition of the whole of the parameter space. And of course, this partition is crucial because for statistical purposes, the whole of the parameter space is relevant, irrespective of whether you're interested in 1 or 2 or 5 or 10 different values. If you want to do a good job, the whole of the parameter space is relevant. So if you view statistical or significance testing within that, yeah, it's a special case of Lehman-Pearson testing where the power and everything else is well defined. And I'm going to surprise some people when I show you Fisher himself talking about power. So I'm going to leave these details out because I'm going to run out of time very soon, and simply focus on this pre-data, post-data. The real difference between the two is not incompatible hybrids or anything else, is that the p-value is a post-data error probability. And that makes it very different, because post-data, we have the observed value of the test statistic. Is that relevant? Yes. The data tell us which tail is relevant. The other one isn't. So if you look at the dx0 here, and it's positive, don't look on the left side. The data tell you the only relevant one is the right side. So anybody who is criticizing Fisher that he had a sort of a tail in mind when he was doing testing, they don't really understand exactly how he was thinking. Yes, post-data, I know in which direction, if there is a discrepancy, where the discrepancy is going to be. So that's really an important distinction here. Now, the p-value was questioned as far back as 1938. Bergson. He basically published a paper and says, every time I look at the results of a Pearson chi-square test, the p-value is smaller every time the sample size is large. So what the p-value tells me is how large the sample size is. Now, there was some truth in that. And the reason is the p-value, of course, depends on the power of the test. And the sample size is a significant contributor to the power. So it's very clear that the old-fashioned statisticians knew that. So they said, if you have a very large sample size, don't use 0.05, adjust it. And even Lehman has some rules of thumb. Other people introduce adjustments. But what we need is really not rules of thumb, but a coherent way of handling it. And the severity evaluation is exactly that. And the intuition behind it is a rejection of the null with a small sample size, let's say of 50, is much better evidence that the null is false than a rejection of the null with 10,000 observations. That intuition is captured by the severity evaluation, and here I have examples to show you how the warranted discrepancy from the null, which is what people should call the effect size, depends on the power of the test, and in particular, the sample size. And that, of course, gives us a way to distinguish between statistical and substantive significance. Statistics can take you all the way to the warranted discrepancy from the null is less than 0.7 something. Then you go to your substantive knowledge and say, is that discrepancy big enough for me to call it substantively significant? You cannot call that out of thin air. You need substantive information to do it. Now, as I said before, people confuse significance testing because it's applied to both during the modeling as well as the inference part. And here I clearly distinguish between the two sides. And it's one thing to construct a model and validate it before you start the inference, because if you haven't, you really shouldn't be using inference and thinking that your error probabilities are the right ones. So this, of course, needs some further delineation, and this is the difference between a statistical and substantive model, which, of course, I don't have a lot of time to say, but the way the two are related is you choose the probabilistic assumptions on the basis of the chance regularity patterns of your data, and then you choose a parameterization that relates your statistical model to your substantive model, and we call that embedding. Now, there is, of course, a huge difference between statistical significance, which is my assumptions, the probabilistic assumptions are valid for this data, and substantive adequacy, which is a completely different thing. So people confuse the two, so they use the box slogan, models, all models are wrong, but some are useful, and they think that's absolution from the scene of statistical misspecification. It's not. Please read George Box. He's very clear. When he says all models are wrong, he means they are not exact pictures of reality. Thank you. That's why we call them models. But he goes immediately and says, test your probabilistic assumptions using residuals. George Box and Jenkins produced the classic textbook on time series with diagnostic testing. So he's not leaving that out. He's talking about how realistic your model is. And substantive adequacy, a completely different ballgame. So is this model substantively adequate if it captures or explains or predicts the phenomenon of interest? It's not whether the probabilistic assumptions you imposed on the data are wrong or not. So in summary, it is one thing to claim that all substantive models are not exact pictures of reality or realistic enough, and completely another to say I've imposed invalid probabilistic assumptions on my data. So a lot of this terminology and the framing is mine, but a lot of the ideas are actually very old. So to make my point here, I have quotations from David Cox's book with my interpretation of what he's saying in square brackets. So he's distinguishing between modeling and inference. He's distinguishing between statistical misspecification, the substantive adequacy, and also some of the other notions are there. Please read it, and you will see what is going on. Now, you have a statistically adequate model. What will go wrong? Well, if you're doing classical inference, then you're relying on sampling distributions. And the formula up there relates the sampling distribution of any statistic to the distribution of the sample. A misspecified model means your distribution you put there is wrong. Your likelihood is wrong, so anything that revolves around sampling distributions and likelihood functions, including Bayesian inference, by the way, is going to be wrong. So Just to give you a glance, here is a simulation. On the left-hand side, I have a statistically adequate model, linear regression, everybody understands that. On the right-hand side, I have a misspecified model. The data have a trending mean, but you left it out. What would be the effect on your inference? On the left-hand side, you can see the means of these simulations, the standard deviations, but much more importantly, right at the bottom two rows, you can see the empirical error probabilities. And you can see the size of the test. And it's very close to the nominal. So one way that misspecification comes up is that when you do testing, your nominal error probabilities and actual error probabilities are very different. So 0.05 is very, very close. And of course, when you go to the right-hand side, you end up with inconsistent estimators that get worse and worse as the sample size increases. And of course, your type 1 error is already 1. You're guaranteed to reject the true null hypothesis 100% of the time. So it doesn't take a lot to destroy the reliability of your inference. Now, when I present this to my fellow econometricians, they say, oh, come on, people don't look at their data if it's trending. Well, they don't. Here I have an example how this can come in. Here I have a typical time series. Somebody is taking differences and says, well, that looks stationary. It isn't. And the only way you can find out is actually to do the testing. So here I have the estimated regression. These people are looking for a unit root. And of course, they're going to conclude there is a unit root. Wrong. And the reason is, when I do misspecification testing using the residuals and an auxiliary regression, there are missing trends, t and a t-square in particular, and that really destroys your inference. So there is reluctance to do all of this. There are many reasons. I'm going to leave them behind and simply focus on assumptions. The top is my way of specifying the linear regression model. All assumptions explicitly stated, and the assumptions include the parameterization. At the bottom is the traditional way in terms of errors. You're not quite sure whether they're all there, but there is a sort of a rough equivalence between the two. I just had to bring it out. So misspecification testing is really testing outside the model with the null being the model is valid. But of course, the right-hand side is non-operational, so we find different ways to operationalize that. And it can take many different forms. You can start with the original model and compass it in a bigger model and test inwards. And that sounds like an Emma Pearson test, but it's not really. Or go for directions of departure. I do both. But in particular, directions of departures using auxiliary regressions. So I'm going to skip all of that and simply show you the kind of auxiliary regressions that can tell you exactly what kinds of systematic information there are still in your residuals that you haven't accounted for. So the numbers at the top are departures from the different assumptions I showed you before. And before I stop, let me give you an empirical example. This is another example from finance. People call it the capital asset pricing model. They regress one variable, which is basically excess returns, on another variable, and the whole thing revolves around linear regression. But of course, they never test their assumptions. And the assumptions is that these are plots of normal IID data. And of course, you can see they're not. If I apply the misspecification test, you can see it falls apart. For those who are interested, there is a long discussion here. And of course, one of the questions you have to be careful is test for substantive adequacy when your model is misspecified. Like, is this an omitted variable? And I have an example there. It will shock you, but in a good way. I also have Yule's nonsense correlation for those who are interested. So there is no correlation in Yule. But the way Yule dug out the assumptions is very impressive. He went backwards. Says, here is a formula. Under what circumstances are these formally relevant for what I want to ask? I have the whole thing here, so if people are interested, I urge them to look at it. So, since I don't have any more time, I'll stop here.